Okay, welcome back for video 2 of integration in polar coordinates. We are ready for step 2, which is to approximate. So we're going to approximate the signed volume that we have over each polar rectangle. So let's just suppose that this is the ijth polar rectangle. So I'm going to pick a representative point in it, which I'm going to call Rij star theta ij star. For short, I'm just going to call that Pij star, but I'm representing it in polar coordinates. Okay, so that's just a point in the ijth rectangle. Okay, now we're basically saying that the signed volume is going to be approximately f of Pij star, that's the height, times delta Aij, times the area of this ith polar rectangle. So what's going on here is the heights that I have may vary. So I might have a curved surface lying above this thing. And of course that's problematic because then we don't have a nice formula for volume like area of the base times the height. So we say, oh rats, the height is changing, I wish it weren't. Let's go into denial. So we look at picking our representative point, we calculate the height at that point, and then we say this whole thing is approximately like the volume we would get if we had a constant height lying over that same polar rectangle. So that's essentially what we're doing. Okay. Now this part we're totally used to. You pick a representative point, you plug in the function at that point, you pretend the height is constant there. What's new is figuring out the area of a polar rectangle. Okay. So let's see if we can't figure out what that's going to look like. Okay. Now, I'm just going to draw a polar rectangle here where this is my theta equals theta 1 and theta equals theta 2. Okay. So I'm just assuming we're going from theta 1 to theta 2. If we're in the ijth rectangle, then theta would actually be going from j minus 1 to j, or the index here would be changing over different values. I'm just supposing we've got 1 and 2. Okay. And then I'm going to call that r equals r2 and r equals r1. So those are my 4 boundaries for this polar rectangle. And I want to try to calculate the area of that thing. Okay. Well, I can say that the area of my polar rectangle, it kind of looks like it's the crust of a slice of pizza. So I can say, hey, it's the whole slice minus the inner slice. And that's going to give me the area that I want, which is kind of nice. So each of these little pizza slice things, we call that a sector. Okay. So this is a sector of the circle of radius r2. This is a sector of the circle of radius r1. Okay. And this angle here, I'm just going to call that delta theta. That's going to be the difference between these two angles. So that's the change in angle over this particular wedge. Okay. That should give us enough information to be able to calculate the area of a polar rectangle. So if I'm looking at the big slice of pizza minus the little slice of pizza, okay, if you don't remember the formula for the area of a sector, that's okay, we're just going to figure it out. I'm going to say this is some fraction of pi times r2 squared. It's some fraction of the area of the circle with radius r2, this bigger radius, minus this is going to be some fraction of pi times r1 squared. It's some part of the entire circle of radius r1. Now for both of them, this angle in here is my delta theta. Okay. So that angle is a portion of a revolution. So to figure out the fraction, it's just going to be that angle over 2 pi, which is the angle that would correspond to a full revolution. So times pi r2 squared minus delta theta over 2 pi times r1 squared. Well, this is very exciting. My pi's are going to cancel. Okay. So what I have then is that the area of this polar rectangle, apparently I should have erased a little bit more, the area of this polar rectangle I can describe fairly nicely as just being delta theta over 2, which I can factor out, times r2 squared minus r1 squared. Now, I can hardly see a difference of 2 squares and not want to factor it, so I'm just going to. So that's going to be delta theta over 2 times r2 minus r1 times r2 plus r1. And this is incredibly exciting because that's the change in r. That's delta r. So I'm seeing delta r and delta theta show up in this formula for the area. This is so exciting. But that's not the only thing that shows up. So when we have rectangular coordinates, the area is just delta x times delta y. Here it looks like we've got delta r, delta theta, and some extra stuff. Oh my goodness. I'm just going to rearrange these things. I'm going to put all the extra stuff together. r2 plus r1 over 2 times delta theta times delta r. That's the average radius. So the area of a polar rectangle is exactly the average radius times the change in angle times the change in radius. Very cool. Now, I'm not going to require that we use the average radius in setting this up because we've already had to choose a representative radius to evaluate the height at that point. So remember, we chose a point Pij star that had an Rij star, was the representative radius, and we use that to evaluate the height. I'm just going to use that to approximate the average radius as well. Okay. So with that, we can say that the signed volume is approximately Rij, let me write it in this order. F of Pij star, that's my representative height, times Rij star times delta r times delta theta. Very cool. Okay. So notice, there's my height. I've got this extra factor of r here. If you remember, when we started talking about integrating in polar coordinates, I said that we were going to require r to be non-negative. This is why. Because we always set up our integrals so that what determines the sign of our signed volume is just the height function. This part represents the area of the base, which we always count as being positive, and so we have to have non-negative r values in order to make sure that the base is non-negative. Should have said non-negative instead of positive. Okay, excellent. Then of course we just add all of these things up. So once again, we're going to be getting basically a double Riemann sum. So we're taking our height times our area. We're going to suppose we've chopped things up into pieces where delta r and delta theta are consistent. That just makes things a little bit nicer. So we're adding up the sum as I goes from 1 to m, and the sum as j goes from 1 to n. So this is varying over all of the circles that we chopped things into, and then this is varying over all of the rays that we chopped things into. This is our Riemann sum that we have, And then step 4 is to take the limit. Now, I'm not going to recopy everything, so I'm just going to put that up here. It becomes the limit as m and n both go to infinity. Of this Riemann sum. So that's how we're going to set things up. Now, you're not going to have to actually set up a Riemann sum, but what this tells me is that if I have the double integral over d of f of xy dA, I can rewrite that as the double integral over d of f of r cosine theta, r sine theta, there's my f of xy right there, r dr d theta. Whoops. Sorry, if I'm writing dr and d theta, this would have to be over appropriate limits. We still have the rule that if we write just one symbol here, we write just one symbol here. If we write two symbols here, we have individual limits on our integration signs. Okay. So this right here is my dA. So there's going to be an extra factor of r that just gets absorbed into the integrand. Pretty cool. We'll see how that plays out in some specific examples in our next few videos. Okay. Yeah. See you soon.